So thank you everyone for making the trek out. Yeah, thank you. Again, thank you everyone for making the trek out, especially Steph, who came all the way from up north, University of Strathclyde. And so Steph completed her PhD in what year?
I have no idea.
Okay, sometime sure, with Viv Kenton, well, at Durham, and then moved up to Strathclyde, where a bunch of lovely physicists are working on quantum computing, including Steph in particular. So we got in touch because we're both part of the CCPQC and started talking about potential projects. And I was like, come on down, let's talk more in person. So Steph will present her work on lazy quantum walks with multi-qubit gates. She'll be here through tomorrow. So if you want to have a chat, just let us know. And let's give her our attention.
Well, thank you so much. Yeah, so I'm going to be talking about specifically near-term quantum algorithms with realistic modeling and specifically quantum walks. But I kind of want to use this as a lens to think about near-term algorithms. This is the paper. Oh, sorry, that doesn't work. This is the paper on arXiv, and these are my funding bodies. Please interrupt me throughout if you have questions, especially if I take something as known when it's not known. So, press the wrong button. It worked last time. It worked a minute ago. Okay. I'll just click the.
Do you want me to click through or you have
Oh, that's fine. Okay. So first of all, I'm going to do a little intro to near-term quantum algorithms. So, what we're usually looking for in quantum algorithms is either quantum uniqueness or quantum speedup. Speedup meaning that we use less resources, for example, time or space. Usually this utilizes the big D to the N mapping of resource to state space. So usually we're talking about qubits, mostly as a holdover from classical computation because that's in bits. But when you have n number of qubits, your state space is d to the n, and it means that you can do multiple operations in superposition. Often it also utilizes quantum entanglement or write-only memory. The quantum entanglement is stronger correlations that you can get than you can get in classical, and write-only memory means that as opposed to in classical, sometimes you will only write to memory of qubits, and then you won't measure those qubits at the end, but they will still have a very important function in the algorithm due to entanglement. They will be entangled with the rest of the, for example, qubits. And then the other important thing about quantum is complex/negative state amplitudes, which can often lead to constructive or destructive interference, as in the case of quantum walks. So hopefully you've seen a Bloch sphere before. So instead of just having 0 and 1, we can have some kind of superposition of 0 and 1. So being in both the 0 and 1 state at the same time with some probability. And then we also have phases, but I'm not going to get into phases today because they're not particularly relevant to quantum walks. Often when quantum uniqueness or speedup is identified in a quantum algorithm, it does not take into account several different things, which really they should take into account. The first one being the readout problem. So the fact that if your result is encoded into many different states, so for example, your result could be encoded in d to the n different states, it means that you're going to need to do in order to read out all of those states, you're going to need to do your algorithm many, many times in order to get all of those readouts. and get a probability distribution. We also need to think about hardware constraints. Hardware does not, in the near term, do operations perfectly, and also different hardware has different abilities of what it can do, more on that later. And then the other one is having end-to-end algorithms. So this means considering state preparation, encoding, decoding, readout. Often the fact that you have to do all of these things as well as your algorithm will kill your speed up or whatever it is that's special about your quantum algorithm. So people are getting better at that in recent publications. But if you're trying to prove some kind of quantum advantage, you really need to include all of the bits from start to finish that you would need to do on the quantum computer, or all of your classical overhead as well, in order to evaluate whether you really have some kind of advantage. Sometimes people miss this out, which is not good. So there's lots of different kinds of quantum hardware. So the actual physical thing that we do our quantum algorithms on. This criteria is a well-known set of criteria of the things that we need to have quantum hardware that will actually perform quantum algorithms. It's largely to do with qubits. So your qubits need to be well characterized, meaning, for example, you have well characterized energy levels in the case of neutral atoms. Scalable, meaning you can have lots of them, and you can have lots of them and they'll stay coherent for a long time. Qubit initialization, they're actually in the states that you want them to be when you start. Long coherence times, universal set of gates operations. I think this maps to classical as well, but there are lots of different universal gate sets. The most common one being, for example, Pauli operators, Hadamard, plus some kind of control gate. And so every piece of quantum hardware needs to be able to do at least one set of universal gate set, and then measurement of an individual. There are lots of different examples of quantum hardware. Specifically at Strathclyde, we're looking at neutral atoms and fermions. And my personal criteria is that it's not good enough for quantum hardware to be able to do this stuff. They also have to be good at something. So they have to be good at a specific algorithm or a specific application. They have to be suited to something. And all of these different hardware are suited to something. People often make the mistake of having hardware agnostic algorithms, but I really believe that as early on in quantum algorithm development as possible, you should be thinking about what kind of hardware you want to be running this on, which hardware is suited to your kind of algorithm or application, and we'll see that on quantum walks. So, background on quantum walks and neutral atoms, because neutral atoms is what we have at Strathclyde, and you can do quantum walks on them. So what is a quantum walk? It's the quantum version of a classical random walk, which is a really, really, really simple method of computation. You have your walk on some kind of graph. So for example, if it's on a line, you start at one point. So for example, origin, this is your walker. You have a coin, you flip it. If it's heads, you go one way in one step. And if it's tails, you go the other way. And then you do many, many steps, many, many flips, and your walker moves around. In classical, which is this blue curve here, where the x-axis is position and the y-axis is probability, you will basically just oscillate around the origin. You won't get very far. However, a quantum walk is exactly the same, except that your walker is quantum and your coin is quantum. So your walker can be in a superposition of positions, and your coin is in a superposition of heads and tails. So your walker will be in many different places at once until you measure. And this ends up having a very different looking probability curve. Specifically, the destructive and constructive interference from the fact that you can have complex and negative amplitudes means that you get a low probability around origin. You get all these spikes and maximums quite far away from the origin. What this actually translates into is a quadratic speed up for search problems. So speed up compared to classical. By speed up, I mean the amount of time that it takes to do your search for a mock state, and exponential speed up for routes across networks. Again, these are in theory. These are not with end-to-end algorithms where you think about state prep, readout, etc. So these are theoretical speed ups, not practical speed ups. Quantum works are also universal for quantum computation, which means that you can map anything you can do in quantum computation into a quantum walk. This means the way that you do this is by having different networks, graphs that you walk the walks on, and having different dynamics for your coin, which doesn't have to be two-dimensional. The coin matches the dimensionality of the graph. And these are some really cool papers that prove all this stuff. Talk a lot about the difference between continuous time and discrete time quantum walks. I'll only be thinking about discrete time quantum walks, as in one flip of the coin equals one step. So the reason that we want to do quantum walks modeled with neutral atom hardware is twofold. The first one is that we want to do it as a toy model for the lattice Boltzmann method, which is a method of fluid simulation. The reason for this is that quantum walks map really, really well onto lattice Boltzmann. So lattice Boltzmann works with transport and collision. This maps exactly onto collision is the coin flip, and then transport is the shift, so the step. And yeah, it maps really, really wonderfully. There's this really nice paper here where called lattice Boltzmann is quantum lattice Boltzmann is on the wall. The other thing that motivates the inclusion of lazy quantum walks in this work is that LBM requires a rest state. This just means that, so for example, if you're modeling fluids in a 2D plane, you have all of these directions, then you also have the possibility of staying still. This is a rest state. And what that maps onto in a quantum walk is just having a self loop on the graph that the walker is walking on. The second motivation is an algorithmic benchmark. In benchmarking, we're trying to compare different hardware. It's really difficult to say what hardware is best. We shouldn't be thinking about what hardware is best. We should be thinking about what specific things or specific hardware is good at. That's what we're trying to show with benchmarking. So two really cool things came out recently. This one from our group in Strathclyde. It shows that this term called the quantum volume, that's to do with finding a number that tries to characterize how much a hardware can do in terms of things like qubit connectivity and stuff. They found that for a 9-qubit quantum processor, it has the same quantum volume as superconducting hardware, which is like superconducting hardware is most common at the moment. It's had the most money going to it, and historically, it's been a better hardware in terms of fidelities of gates. So when you do an operation, is actually doing what you expect it to do. But other hardwares are catching up in that regard. The other thing that this paper looks at is when doing the Grover's algorithm, really important quantum algorithm, CZ gates versus CCZ gates. So whenever you have a quantum circuit, it will look like this. The number of qubits that an operation is applied to the native operation. Okay. Each hardware has different ranks of operations that they can natively do. So in superconducting, they can only ever have two qubits interacting at once. And so if you want to have, for example, 4 qubits interacting, you have to pairwise interactions all the way up into 4-qubit interaction. But for neutral atom hardware, they have native multi-qubit gates. So for example, this is a 3-qubit gate. And so they looked at, with current neutral atom hardware and current fidelities of multi-qubit and 2-qubit gates, is it better to do native 2-qubit gates or native 3-qubit gates? And we found it was better to do native 3-qubit gates. Another full benchmarking paper looks at nearest neighbors versus all-to-all connectivity. Another really cool thing about neutral atom hardware is that once you have your array of neutral atoms, you can just pick them up and move. Usually, if you want a qubit, so for example, in superconducting, if you want a qubit here to interact with the qubit over here, you have to do a bunch of swap gates in order to get in with the qubits in between, in order to get them to interact. But with neutral atoms, you can just pick it up, put it over here, do your 2-qubit or whatever gate. And so they looked at nearest neighbor versus all-to-all connectivity, found that all-to-all connectivity is better, meaning that they have higher fidelities at the end of their algorithms, as in it's closer to what we wanted it to be. The other paper that came out that's really important to this work is the CPTN maps. So that means completely positive trace non-increasing maps. It's basically just a way of modeling these gates. And it means that we can do realistic error modeling for these multi-qubit gates, which we use in this work. So because quantum walks look like this, so I'll go into this circuit model a bit more later, but because they have these big, high rank multi-qubit gates, quantum walks as a benchmark encompass multi-qubit gate fidelity, effective or native. So native meaning you can actually do that multi-qubit gate, effective meaning you have to do lots of native multi-qubit gates to make up the effective gate, qubit connectivity, and then the normal stuff like qubit coherence, how long your qubits last, and span, which means state measurement. So all of the inputs in this work are pure qubit states, which means they look like this. You have your amplitude of your state in 0 plus your amplitude in 1, where the amplitude is related to the probability of finding that qubit in that state. And therefore, amplitude squared always ends up to 1. Multi-qubit states look like this. And again, importantly, your amplitudes can be complex and negative. The set of gates, so the set of operations that we'll be looking at, that we'll be using, look like this. An X gate is just like a NOT gate. It just flips your states. This is a rotation in Y. It basically, if you apply this to a qubit not in superposition, for example, to a 0, it turns it into a superposition between 0 and 1 with amplitudes with a ratio to do with theta. And then very, very importantly, we have, so these are single qubit gates. They apply to single qubits. These are 2-qubit gates. They apply to 2 qubits. So a CX gate is a control X gate. It just means that if you apply it to 2 qubits, if and only if the first qubit is in one state, then you not do X the second qubit. And then the same idea for the CZ gate. If all of your qubits, if both of your qubits are in one, then you minus the amplitudes. Control gates are really, really important in quantum computing. They generate entanglement. They are part of a universal gate set. And then we also have multi-qubit CKX and CKZ gates. So this just means that we have more controls. So the control qubit is the one that, for example, has to be in one, and the target qubit is the one that actually gets changed. These just have multiple controls, so they all have to be in one for the last target qubit to be, for the X gate to be applied, and so on. Cool, so we're doing encoded quantum walks. So that means that we aren't physically doing a quantum walk. So our qubits aren't physically moving. Instead, the amplitudes are the things that are moving around the ring. And we do rings, so it's just like a line, but with slightly boundary conditions. And then you need log big N qubits in order to encode n nodes in your ring. So for example, for a 4-node ring, you need 2 position qubits. And then you have 1 coin qubit, which is just whether it goes clockwise or anti-clockwise. And then a lazy quantum walk, as I said, is exactly the same, except that you're walking on a graph with self-loops. So it has a chance of staying in the same place. And you could, in order to do this, you need to increase the dimensionality of your coin. One way that you could do this is you could have a Q-trip, so a 3-dimensional coin. So you could have a state, you could have a Q-trip that has 0, 1, and 2 states. But because we're doing near-term modeling, we're only using qubits, and therefore we have 2 qubits, one which is our usual, decides whether it's going clockwise or anti-clockwise, and one that decides whether it's resting or stepping. So this is what our gate model of a quantum walk looks like, specifically a 1-qubit coin quantum walk, so standard quantum walk. So these are our position qubits. You have little n position qubits, where again, you're on a graph of 2 to the n nodes. Then you have your 1 coin qubit, and then this is your flip of the coin. So you rotate your coin, and it's the same thing as flipping it. We're specifically doing a rotation of y with pi over 2, which just means that it's symmetric. So you have an equal probability as going clockwise as you do anti-clockwise. So it is like a normal coin, the 50% heads, 50% tails. And then we have our increment, which means going clockwise. And it's made of these huge, many-controlled NOT gates. So these dots here indicate controls, and then this circle with a plus in indicates a target. And so you need an effective n+1 qubit gate, and then n-1 all the way down to a 2-qubit gate. Yeah, and then you do the decrement, which is the exact same, except you have a bunch of X gates, NOT gates for them. These two will cancel out, but it's just easier to represent dots. Have those in there. And then at the end, you only need to measure the position qubits, but because this is a quantum circuit and it's all probabilistic, so for starters, this is just one step. So we'll have to repeat this circuit for however many steps of the walk we're doing, and then when we do our readout, we will only get one output. So for example, let's say we have a 3-qubit state and we read out 0, 0, 0, and then we have to repeat many, many, many times in order to get to some accuracy all of the outputs that you could possibly get, find out what the probability of getting each of those outputs is by doing it many, many times. And then therefore you get your probability distribution, and that is your answer. The gate circuit for a two-qubit coin quantum walk, aka a lazy quantum walk, is very, very simple, very, very similar, except we have this extra coin qubit. We flip it the same as we flip the other coin, and then we just control everything that we did in the standard quantum walk on this coin. So when this coin is in state 0, none of this will happen because 0 denotes the rest state of staying, and therefore we don't want any of this stuff to happen. But then when it's in the 1 state, all of this stuff happens as normal. That means that we require gates of greater rank. So by rank, I just mean how many qubits it's applied to. And again, these are effective gates, not native gates. They're not what we're actually physically doing in the hardware. They're the number of qubits that have to interact in total. And so we just plus 1, so it's n plus 2 qubit gates. And qubit gates. And then we have to think about gate decomposition, that this is mapping our effective gates to our native gates. As I will mention in a minute, we have we consider up to 4 native 4-qubit gates in our model. And so when we have these big effective gates of 5 qubits or more, we have to decompose them into lower rank gates. And that increases our gate depth. So that increases how many operations we have to do. And it's just a lot of gate maths. This is the scaling in terms of CKX gates, in terms of the number of controls. But yeah, basically the higher rank of your native gates, the lower your gate depth, because you don't have to decompose them so much. So specifically, our modeling is neutral atom modeling. The neutral atom quantum device that we have at Strathclyde is specifically cesium atoms trapped in a triangular array. Also in my model, I consider a rectangular array. So this is what a triangular array looks like. Rectangular array would just be this. And then we have 2 well-defined, high-defined states, R0 and R1, that form our computational basis. So this is the only states that we have in our gate model. But when we actually do operations on our states, we have to go via this Rydberg level, which is just a very highly excited state. There's also an intermediary excited state E, but we don't need to worry about that. These really high-line excited states experience dipole-induced pairwise interaction. So basically, if you have 2 atoms that are next to each other, or more specifically within the Rydberg radius of each other, then their Rydberg states interact such that you can only have 1 Rydberg excitation within the Rydberg radius. So if, for example, you have 2 atoms within the Rydberg radius, and one of them is already in the Rydberg state, and then you try to pulse your second atom up into the Rydberg state, and specifically one state and the Rydberg state are coupled together. Can't go straight from the 0 to the Rydberg state. If you try to pulse the second atom up into the Rydberg state is detuned, so it's at a higher energy level. So it means that it won't actually arrive at that energy level, and it will fall back down into the one state. And this is how we do control gates, which again are very important. The same thing is true if you just have more qubits within the Rydberg radius. So here you can see you can have 3 qubits inside the Rydberg radius. In principle, the amount of qubits that you can have within the radius is only limited by your geometry. So in a 2D array, you can have, at the moment, a maximum of 4 atoms within your Rydberg radius. But you can imagine that if you had a 3D array, you can get more with the same radius, and therefore have higher rank negative gates. Cool. But these operations aren't perfect, as in, even though for our CZ gate, we're trying to go from these states to these states, in the lab, this doesn't happen perfectly. This is what we mean by gate errors. These gate errors come from spontaneous decay from the excited state and Rydberg state, so they fall down into the ground state even though we don't want them to, and from the finite blockade radius. So that means that when we have the blockade radius like this, there's actually a tapering off of the pairwise interaction between the Rydberg states. And so even though in this diagram the atoms are far away from the center, you actually want them closer into the center, but you still want to be able to individually address each of the atoms. So there's sort of a balancing effect going on here of having them not too close that you can't individually address them, but not too far away that you're getting too much error with your qubit operations. And then we model these imperfect operations with affected matrices that look like this. So again, these are CPTN maps, which means that they're physical. They're describing what's physically going on within the hardware. I just call them affected matrices because it's easier to say. So our CZ gates look like this, and our CCZ gates look like this. And then we also have C3Z gates, but it's too long, so I haven't put it on the slide. And I just want you to see that largely the error that we're getting here is in terms of how many ones you have in your state. So how many times you have to excite from 1 to the Rydberg state, and that determines largely what your error is. So usually you would want 1 here, and yeah, so that gives us fidelities that look like this, where fidelity is defined like this. It basically means how close to the operation that we actually want to be happening with all the ones, well, sorry, actually all the minus ones, is the actual physical gate that we're doing in the hardware. So for example, the 2-qubit gate has a fidelity of 99.81, which is actually really impressive for quantum computing. I mean, for classical, that probably looks really terrible. You're looking at way above 4 nines. But for quantum computing, that's actually pretty good. And then for 3-qubit gates, 99.54, and 4-qubit gates, 98.50. And then single qubit gates, like Power gates, hard mod gates, have 99.99 fidelity, which we approximate to 100. We just, for the sake of simplicity, we're pretending that we have perfect single qubit gates. Again, 4 nines in quantum computing is really, really good. Doesn't sound right in classical computing, but that is near perfect for us. And that means that the fidelity of control Z gates is equal to control X gates, because to transform between them, you need to use single qubit gates. Cool. And then part of our error model, aside from our gates, which comes from this paper here, and it's all to do with physics modeling. So unlike most error modeling, which comes from just doing it in the lab and then figuring out how close what you wanted it actually is, this instead is physics modeling with the knowledge of, for example, laser power. We can actually do in the lab to figure out what the best case is for what we can currently do in the lab. So if you look in the paper, you will see some fidelities of what we've actually achieved in labs around the world. They come close to this, but not quite this. So again, this is ideal case for what we can currently do in the lab, if that makes sense. And then also part of our model is spam, so state measurement, and passive/waiting noise. So qubits, when they're not being acted on, don't just stay in the states that you left them in, they decay. And so we have to factor in that noise as well. Cool, so finally, simulation results. So again, we use this noise model, and we do what basically is a matrices and vector simulation to find out what we would expect if we were to run quantum walks in the lab. What would the results look like, as in how close are the results to what we expect them to be? Or more accurately, what we want them to be. So on the x-axis, we have the number of steps. So again, each of that gate circuit, that was one step. This is not, this is, so for example, a simulation of 5 steps, you run it for 5 steps and then you measure it and then you get that result. It's not, this is not representative of if you ran it for 21 steps and this is what it was doing for those 21 steps. You measure at the end of each run. And then on the y-axis, we have the Helena final state fidelity. So again, it's how similar is the output that we got to the output that we wanted. A fidelity of 1 means it's exactly what we wanted. A fidelity of 0.5 means that it's orthogonal to what we wanted. So it's not opposite to what we wanted, it's like right angles to what we wanted. And then 0 is opposite of what we wanted. So basically, 0.5 is garbage, and anything before 0.5, anything lower than 0.5 is worse than garbage. We have on here, as well as the simulation results, we have the real superconducting results in the x's. So this isn't exactly a faithful comparison because these are real superconducting device results. And these are simulation results, but it still gives you kind of an idea of a comparison between the two. So for example, with these superconducting results, you get massive decreases in fidelity after just 1 step. That's because the state preparation for superconducting, and specifically in the IBM computer, is really, really bad. So I'll describe the sizes. So these ones in pink are on a 4-node ring, in blue on an 8-node ring, in yellow on a 16-node ring. Unfortunately, the IBM results don't have the lazy versions of the quantum walk thing. You have the standard versions. The ones in dots are the standard one qubit coin versions, and the ones in triangles are the 2 qubit coin lazy quantum walk versions. So first of all, looking at the superconducting results, you can see that for on 8-node or 16-node, they immediately go below the garbage line. That's why I think there's this great amount of fluctuation going on, because it's just Like it's not physical. It's just fluctuating how much garbage it is. Whereas this 4-node result is more physical, and it is telling us more about how well the quantum walk is actually performing, why it goes down and then back up. I'm not actually sure. I suspect it's because if we had error bounds, they would be really, really big. Okay, so our neutral atom results. So we're specifically using this native gate set here with 2-qubit gates and 3-qubit gates. So we're not yet using the 4-qubit gates. Everything is decomposed down into 2 and 3-qubit gates with these fidelities here. And so first of all, we find that these fidelity results group together. So the quantum walks that require the same maximum effective gate ranks, those are grouped together. And that's because the hugest amount of error, the largest amount of error, comes from the imperfect gate fidelities. The second biggest amount of error is from the readout. Cool. We can also see that for a quantum walk of 21 steps, the 4-node and 1-qubit coin 8 nodes are actually kind of doing quantum walks all the way through the 21 steps, but the larger quantum walks are not. They're so bad they're not even doing a quantum walk by the 21 steps. But if you were to look at really tiny numbers of steps, like 1 or 2, they are still sort of doing a quantum walk. So basically, we could do these really tiny, teeny tiny quantum walks on the quantum hardware today, and we would actually be doing a quantum walk. So the next thing that I looked at is increasing the native gate set. So now we have access to 4-qubit native gates. In decreased opacity, you can see the previous results from the previous slide, and then in increased opacity are the new results with the larger native gate set. You can see that it improves the final state fidelity quite a bit, to the point where we're not really improving whether we're doing a quantum walk or 21 steps, but we are improving, for example, how many steps we can do before we go under 0.9 fidelity. Yeah. The other thing that I looked at was what if instead of introducing the native 4-qubit gate, which, for example, we haven't actually done in the lab yet. At Strathclyde, they only do 2-qubit gates so far, and in the world, they've only done 3-qubit gates. So what if instead of introducing the native 4-qubit gate, we instead just improve the fidelities of the 2 and 3-qubit gates? The way that I've modeled this is not physical like the effective matrices that we saw earlier. I've basically created fictitious effective matrices that try to follow the same patterns that the real physical effective matrices follow, but they are still fictional effective matrices and therefore fictional fidelities. But it gives us sort of an idea of what we would get in terms of final state fidelity. These fluctuations here are an artifact of the way that the effective matrices look. If you have supersymmetric effective matrices, meaning that all of the amplitudes, all of the elements in your effective matrices are equivalent to each other, then you get much smoother lines. So this is an artifact of that. I've tried to make it as physical as possible. So this blue line is the with the native 3-qubit gate, and this gray circles is with the native four-qubit gate, and the fidelity line roughly matches up with increasing the 2 and 3-qubit gate fidelities to 99.99 and 99.79. These are considered pretty unachievable in the near term. So this is as good as single gate fidelities are currently. We hope to get there someday, but in the near term, it's just isn't feasible. And therefore, we conclude it would be much, much easier to just include these 4-qubit gates of much lower fidelity, much more achievable fidelity in our gate set. The final thing that I looked at was, do we have to increase our native gate set forever? So when I found that for doing quantum walks that require 4 qubits, that we want 4-qubit gates, that's a bit of a worry. To do quantum walks, do we therefore need the same rank of native qubit gate as we have qubits? That would be a worry, that would be bad, because our native qubit gates will not scale forever. It is restricted by the architecture of our neutral atom arrays. And so what I've looked at here is, again, this is prediction, this is not physical. So again, these fidelities, these gate fidelities are not from physically derived effective matrices. This is purely just composite fidelity, which is you take the number of gates that are required for a specific quantum walk of a specific size, and then you times together all of the fidelities to get the composite fidelity. So this is very rough, but hopefully it will give us a bit of an idea. And so, and again, rank is the number of qubits that the gate is applied to. So on the x-axis, we have the native gate max, native gate rank that we're accreting from 2. So for example, if you go from only 3-qubit gates to, well, 2 and 3-qubit gates to 2, 3, and 4-qubit gates, and so on. And then on the y-axis, we have our average increasing composite fidelity. We find that there's comparatively huge increase if you go from 3 to 4, and then comparatively small increase for the other increases of native gate rank. This is really encouraging. It means that hopefully introducing native gates, native 4-qubit gates is the sweet spot, and we don't have to keep increasing our native gate set forever. Yes, and also these are the sizes of these quantum walks, where little n is the number of position qubits and big N is the number of nodes in your graph. So we're kind of looking at more interesting quantum walks, but still, if you were to apply it to, for example, fluid simulation, as is Boltzmann, you'd still want much bigger graphs. So, in conclusion, on the near-term quantum walk side, if we're doing a 2-qubit coin quantum walk on a 4-node ring, if you have these near-term accurate fidelities for 2-qubit and 3-qubit native gates, then you get a fidelity, final state fidelity of above 0.99 for 2 time steps and above a fidelity of 0.9 for 14 time steps. We can increase this to 5 time steps and 20 time steps, either by increasing our native 2-qubit, 3-qubit gates fidelities to these, which is somewhat unattainable in the near term, or we can simply introduce our native 4-qubit gate with this fidelity. Therefore, native 4-qubit gates are highly beneficial for the implementation of quantum walks. Native 5-qubit gates and greater ranks probably won't give so marked an increase in final state fidelity. And so we hope, we propose that native 4-qubit gates are the sweet spot We really want labs to have these native 4-qubit gates and for us to give quantum walks a go. And then second conclusion on near-term algorithms as a whole. Certain algorithms are suited to certain hardware are suited to certain algorithms. We should be learning, as theorists, we should be learning more about hardware and hardware capabilities. For example, things like native multi-qubit gates, qubit connectivity. All of these things are things that we need to be aware of when we're developing quantum algorithms. When you see complexity scaling analysis or resource estimations, check whether they have end-to-end analysis, because otherwise it doesn't necessarily mean much. It's a good indication that there might be a quantum advantage there, but it's not proof of a quantum advantage. In the near term, gate fidelity is more important than the number of qubits. Quantum companies especially love to talk about the number of qubits in their arrays, and that will, in the further term, be really important for error correction, because error correction requires a polynomial increase in the number of qubits. But in the near term, specifically, gate fidelity is a lot more important than the number of qubits. And all of this that I talked to you about today doesn't include error correction. And the next big thing with this project to do would be to include near-term error correction, and hopefully we'll see much improved quantum state fidelities. Lastly, I want to plug this review here by some people in our group, Rhonda and my PI Viv. It's a very level-headed look at quantum algorithms, both in the near term, I've talked about today, and in the further term. It talks about where quantum computing might actually find an advantage, not in over-promising way, but in an actual evidence-based way. And yeah, I would recommend it highly. Thank you very much for listening. Any questions?
I think we had stuff to talk. I don't think I will stand up. I don't know. I feel very sticky. This room is weird. Are there any questions online? Are there any questions in the room? I can start us off with a few questions. Oh, Auntie, were you going to say something? No? Okay.
No.
Andy, can you hear us? Do you want to talk?
I guess these empirical numbers that you come up with for these, essentially the accuracy of these particular operations, these are just empirically discovered. Is that what you're saying?
So they're not based on results from the lab. They're based on physical modeling of exactly how you do the operations and things like how good we know our lasers in the lab and stuff are.
Okay.
So yeah, I would highly recommend looking at that paper by Jared in our group. It talks in detail about.
I guess what I'm really asking is, what is the scope for increasing the fidelity of these devices?
So there are things like increasing the laser power. There is things like changing the geometry of our arrays. So for example, those were based on 2D triangular and rectangular arrays. But if you were to do 3D arrays in pyramid shapes, so specifically for native 4-qubit gates, you can imagine your qubits arranged in a pyramid. That would have higher gate fidelities. They're also looking at dual species arrays, meaning that you don't just have cesium atoms, you have other atoms of another element, and one element will be the control qubits and one will be the target qubits, stuff like that. So there is things that we can do to increase the fidelities. Yeah.
Okay, thank you.
On that note, I'll try to formulate the question well. So, so you just described a lot of physical ways to improve fidelities. Are there algorithmic ways that we could, for example, we know that they have this loss. Is there some way you can algorithmically bring some fidelity back in with some other kind of operator that picks up where they, because no matter what you implement, as you apply the gate over and over and over again, things get worse
Yeah.
because
So
it's exponential. So is there some other thing we can apply that tidies it up? Maybe it's a really expensive operation that happens every few applications.
yeah,
but-
so you're kind of talking about error correction.
Oh, is that it?
So
But that means you add a bunch more qubits.
Yes.
Right? Okay.
so
Not
the-
necessarily a new gate or a new operation.
no,
Okay.
no. So within a specific hardware, no, I don't know of propositions to change how we do the gate or adding an operation on or anything like that. The things that come to mind are error correction or like decomposing the gates in different ways. So I showed you this. This is like the standard way to do decomposition, but people are coming up with cleverer ways to do gate decomposition. But no, not in the way that you described.
But the point of other gate decompositions is just to reduce the total number of gates.
Yes.
Okay.
Yes.
Yeah, so you still have exponential problems. Once this
Yes.
runs long enough, everything goes to crap.
And that's why error correction is going to be absolutely vital, because as you can see from the fidelity results, like without massively improving the gate fidelities, it's just not scaling to bigger systems. It's just not going
Yeah.
to work.
Yeah.
So yeah, that's why error correction is going to be absolutely vital.
And for the plots where you were comparing your modeling with some actual, the first one. You said that this was, so the ones with the X's were on.
Superconducting on IBM.
Okay,
So
but you're,
superconducting hardware, IBM quantum.
but you're doing neutral atoms, so what,
Yes.
does it make sense to compare the two?
It does. The reason it's not a faithful comparison is because it's real and
Yeah.
simulated.
Okay,
If we didn't have that problem, then the whole point of benchmarking is comparing the same thing on different hardwares.
and you can't implement this on neutral atom hardware yet, it's just not, it's not ready yet.
So, I mean, you could, but you would have to decompose everything down to 2 qubits, 2-qubit gates in the case of Strathclyde, or 3-qubit gates in the case of America. And I think we need native 4-qubit gates before we even.
But
really
this
bother.
is just, these are 3-qubit gates.
Oh, for this.
Yeah,
Well, yeah, we could do this. Oh, yeah. We could
yeah,
do
so
this.
that's what I was wondering,
I
like
see.
this one, could you get?
This one we could do.
Uh-huh.
A lab in America. I can't remember the Lucan group. I think they could do this right
Okay.
now.
I see.
But they probably would look at something like this and not bother. maybe do the 4-node one, which only requires 3 qubits,
Yeah.
but that would be so proof of principle. Like, so, I mean, again, as a benchmarking, if you could get a bunch of different hardwares together and say, we're all going to do the 4-node
Yeah.
version,
Yeah,
then maybe, but I think they would not see
yeah,
too much of an application for it.
it's just shocking how terrible you said this is because of state prep.
This huge state prep.
Do you assume perfect state prep in the?
No, the state prep.
Oh,
Neutral atoms are just better at state prep.
sorry, I mean, this is slightly, this is going off that last question rather than too relevant to this, but when you're sort of saying that that some places just sort of wouldn't bother doing the actual empirical measurements, is how expensive is it to actually do something like, for example, what IBM did to benchmark these kinds of things?
I wouldn't say it's expensive so much as for something like Kirk. So IBM is commercially available. It's more that everybody's trying to buy time on IBM, and so they did this. I just think that atoms, they would be just looking for something with nearer term applications.
And you can't rent time on this American system.
No. No, that's at a university. That's not commercially available. So neutral atoms are becoming more commercially available, but they're behind superconducting because again, the gate fidelities for neutral atoms were really bad until the last few years, which we've improved up to this sort of thing. And so there's been a lot more interest in neutral atom computing. And so at the moment there's continuous time neutral atom computers that are available to work on commercially, but not discrete time like I do here. Hopefully, again, next couple of years, they'll be commercially available. And then I can apply to do something like this. I have applied to do it on ions. So in the next couple of months, I'll be doing this on ions and we'll see how they compare. But again, it's not super faithful to do real simulated comparisons.
And on those ions, can you do the 4-qubit gates?
So they don't yet. So in principle, yes, but not yet. So ions are the same in that you can do multi-native qubit gates, and you can. I also believe you can move them around so that you have increased connectivity as well, instead of having to do all the swap gates. So yeah, ions and neutral atoms are very similar in the way that they function.
Are there any other questions online?
Can I ask one other thing? And that is that one of the very optimistic things you said was you showed results that essentially imply that when you get to 4, that'll be a sweet spot. That's very encouraging that it's not, you know, way beyond, because one really has no idea.
So I would really like for somebody to, maybe Jared, to make more of those effective matrices. So those physically informed effective matrices for greater rank native gates. And then we can verify something like this. This is very sketchy.
I understand.
Results.
I understand.
But it is, yeah, it is still super encouraging. Yes, definitely.
Oh, interesting.
Well, I don't want to keep everyone here forever. We are out of time. So thank you again, Steph, for coming. I will stop recording.